Exponential and logarithmic equations and inequalities.
We'll start by defining a logarithmic equation. A logarithmic equation is an equation containing a variable in the logarithm. Here are some examples. Log base 3 of x equals 27, or log x plus log of the quantity x plus 2 equals 5. In each case, a variable is inside of the logarithm. Let's take a look at the strategies we're going to use for solving a logarithmic equation. The first strategy is we want to use the definition of a logarithm to rewrite as an exponential. So in other words, if I have y equals log base b of x, that's the same as b to the y equals x. Or we can exponentiate both sides using the base of the logarithm. And the second strategy is, if possible, we want to rewrite, using logarithmic properties, as log base b of f of x equals log base b of g of x. Because since these have the same base, we can simply set the two insides equal to each other, solve for when f of x equals g of x. So we'll take a look at solving logarithmic equations with both of these strategies. Now, an important note is that we have to check our solutions are in the domain of the original logarithms, because logarithms have a domain restriction. We can only have positive values inside of a log. Let's take a look at our first example. We want to solve log base 4 of the quantity x minus 2 equals 3. Since I only have one log involved, I can go ahead and rewrite this as its exponential form. So I can go ahead and take the base of the log 4 and rewrite this as 4 to the third power. So what the logarithm equals becomes the exponent. 4 to the third equals the quantity x minus 2, the inside of the log. And now, since the log is no longer part of the equation, I can simply solve for x. So 4 to the third is 64 is equal to x minus 2. And then I can add the 2 to the other side, so I end up with x equals 66. And there's no problem with plugging 66 back into this logarithm. 66 minus 2 will create a positive number inside the log. So 66 is my answer. Now, that was one way of thinking about how to solve this logarithmic equation, rewriting it in its exponential form. But an alternate way to think about solving the same equation is to exponentiate both sides. So since the log has a base of 4, what I can think about doing is writing this as 4 to the power of log base 4 of the quantity x minus 2 equals 4 to the power of 3. This is called exponentiating both sides. And this helps because we know from a log property that 4 raised to the log base 4 will cancel out and give us just the x minus 2. And then the right-hand side is 4 to the third, which we said was 64. So we obtain our same answer of x equals 66. So this is two different ways of thinking about applying that first strategy. So we end up with the same answer of 66. Now let's go ahead and solve 4 times the natural log of 3x equals 8. So here, the first thing we want to do is go ahead and get rid of this 4 that's in the front of the natural log, because I do want the log by itself in order to use either of the strategies that I used in the previous example. So here, I have two choices. I can go ahead and take the 4 and bring it to the exponent of the logarithm, because that's a property. But since I have an equation here, since this is just 4 times the natural log of 3x equals 8, I can simply divide both sides by 4. So I'm going to divide both sides by 4 as my first step to get the natural log of 3x by itself. It equals 2. And now I want to go ahead and think about either using the definition of a logarithm and rewriting it as an exponential, or exponentiating both sides. So I'm going to choose to do this one by exponentiating both sides. So here, the base of natural log is e. So I'm going to take e to the natural log of 3x equals e squared. And now e to the power of natural log cancels out, and we end up with just 3x is equal to e squared. And then I'm going to divide both sides by 3 to end up with x equals e squared over 3. And here I want to just make sure that substituting this into the original logarithm won't create a negative, and it won't. So if I plug in e squared over 3, the 3's will cancel. I end up with just e squared on the inside, which is a positive number. So this is fine. This is my answer, e squared over 3, or I could think about it as 1/3 e squared. So here I just want to point out that we are, again, exponentiating both sides. We don't want to say we're multiplying both sides by e. We are putting the natural log of 3x in the exponent of e, and we're putting 2 in the exponent of e, so we can apply our log properties. In this next example, we'll solve log base 2, and then I have this product inside the log. I have the quantity 3x minus 7 times the quantity x minus 4, all that's in log base 2, equals 3. So I still just have one logarithm equals a number, so I can use either the idea of rewriting this as an exponential expression or exponentiating both sides. So it doesn't matter how I think about it. I don't have to do it both ways. So since on the last one we exponentiated both sides, here I'll think about it as rewriting it as an exponential. I'll take the 2, the base of the log, raise it to what the log equals, 2 to the third, equals the inside of the log, so that would be this whole product, quantity 3x minus 7 times the quantity x minus 4. Oops. Alright, so now it's a matter of solving this equation. So 2 to the third is 8. I have 8 equals the quantity 3x minus 7 times the quantity x minus 4. So the most common mistake here is going to be setting each of these factors equal to 8. I cannot solve a quadratic equation by setting factors equal to anything other than 0. So unfortunately, what we are stuck doing here is on the right-hand side, multiplying everything out, distributing. So I'd end up with 3x squared. Outer is going to be minus 12x. Inner is minus 7x, so minus 19x. And then plus 28. And then I'm going to subtract the 8 to the other side because I want this quadratic equation to equal 0. So I have 0 is equal to 3x squared minus 19x plus 20. So now I have a quadratic equation set equal to 0, so I should try to factor, and if it doesn't factor, then I can use the quadratic formula. So let's try to think about whether or not this factors. So we can go ahead and think about, are there two numbers that multiply together to give me 60, 3 times 20, and that add together to give me negative 19? And the answer is yes. To get 60, I can multiply negative 15 times negative 4, and that will add together to be negative 19. So we know that this does factor. We could also have just sat and tried the guess and check method, right, if we wanted to. So that wouldn't be so terrible because 3 is a prime number, so we have just 3x and x, and so we'd have to try out different values for multiplying to get out 20. So negative 5 and negative 4 in this case is what's going to work out, because outer is negative 15x and inner is minus 4x, so adding those together gives us that negative 19x. So here is my factorization. So my two possible solutions, setting each of these factors equal to 0, are x equals 4/3 and x equals 5. And I say that these are possible solutions because we need to make sure that neither of these values makes the inside of the logarithm negative, because I can't plug negative values into a log that's outside of its domain. To check each answer, I want to substitute them into each x to make sure the whole inside ends up being positive. So when I check 4/3, 3 times 4/3 is 4, and 4 minus 7, that's a negative. So I'm doing a little sign analysis here. I have a negative, and then 4/3 minus 4, that's going to give me another negative. So altogether, that would make the inside of the log positive, so 4/3 is a solution. And if I try x equals 5, 3 times 5 is 15, minus 7, that's 8, so that's a positive. And then 5 minus 4 is positive. So 5 checks out as well. So I have two solutions to this logarithmic equation, 4/3 and 5. In this next example, I want to solve log of the quantity 3x plus 2 plus log of the quantity x minus 1 equals 1. Now this is different from our previous problems because I have two logarithms involved in the problem. So what I want to do when that happens is I want to see if I can apply any log properties because I want to have just one log, if possible. Now here, because I have logs with the same base, they're the common log, log base 10, and they're added together, I can go ahead and combine these with a log property. This left side will turn into log of the quantity 3x plus 2 times the quantity x minus 1 is equal to 1. So whenever I have logs with the same base and they're added together, I multiply the inside of each log together to form one log with the same base. And now that I have one log with base 10 of a quantity equals 1, I can use either the idea of exponentiating both sides or rewriting this as its exponential form. So here I have log base 10, so I can think about this as 10 to the 1 is equal to the inside of the log, the quantity 3x plus 2 times the quantity x minus 1. So it's a lot like the last problem now, where I need to go ahead and distribute on the right-hand side. So 3x squared, outer is minus 3x, inner is plus 2x, so minus x minus 2. And then we'll subtract the 10 to the other side. I need a quadratic to equal 0. So I have 0 is equal to 3x squared minus x minus 12. And so now we have to determine whether or not this factors. So there are two numbers that multiply together to give us negative 36 and add together to give us negative 1. And the answer is no. So the only way to get negative 36 is going to be negative 6 and 6 and negative 9 and 4, or negative 12 and 3, or 36 and 1, or 2 and 18, but none of those are going to add together to give me a negative 1. So this does not factor, and that means that to solve it, we need to use the quadratic formula. So to solve it using the quadratic formula, we have x equals negative b, so negative negative 1, plus or minus the square root of b squared, negative 1, quantity squared, minus 4 times 3 times negative 12, all over 2 times 3. So simplifying this, we get 1 plus or minus the square root of, now here on the inside I have 4 times 3 is 12, so I have negative 12 times negative 12, that's 144. And that's positive, and then this would be a positive 1, so we have 145, and then all over 6. So I have two different answers here. What I have is I have 1/6 plus the square root of 145 over 6 as one answer, and my other answer, potentially, is 1/6 minus the square root of 145 over 6. And so now I have to check whether or not these possible solutions would create a problem in either of my original logarithms. So I don't want to check it inside of the combined version. I always want to go back to the original equation, and there are two insides to think about here. I have to think about what happens when I substitute these numbers into 3x plus 2 and x minus 1. So here, we want to have a little bit of number sense to determine approximately what values these are. So let's think about the square root of 145. That's a little bit bigger than the square root of 144, which is 12. So this is a little bigger than 12. So 12 over 6, that's 2, plus 1/6, So this number is bigger than 2, and it's positive. So there's not going to be a problem plugging it into 3x plus 2. That's still going to be a positive on the inside. And since this x value would be a number bigger than 2, then if I subtract 1, that's still going to be positive. So 1/6 plus the square root of 145 over 6 checks out. That is a solution. But now here I have 1/6 minus, we said this was a little bit bigger than 2. So here if I take 1/6 minus a number a little bit bigger than 2, that's still going to be a negative number. So that's going to be a problem. If I jump right over here to this log, I have x minus 1. So since this will be a negative number, a negative minus 1, that's going to make this inside negative. So if I can't plug it into both of the logs, then I have a domain problem, and this is not a solution. So this only has one solution, this equation, and it's 1/6 plus the square root of 145 over 6. Let's take a look at another example. We want to solve 7 times the natural log of the quantity x squared minus 1 equals 28. So here I have just one logarithm, so I want it by itself. So I want to get rid of this 7, and I'm going to divide by it. So I'll start by having the natural log of the quantity x squared minus 1 is equal to 4. And then to get rid of the natural log, I can either rewrite this as an exponential or think about exponentiating both sides. But it's typical for trying to eliminate natural log to think about it as the exponentiating both sides situation. So since the base would need to be e, we're going to take e to the natural log of x squared minus 1 equals e to the 4th. So I'm going to end up with just on the left-hand side, x squared minus 1, because e to the natural log directly, right, there's nothing in front, there's just a 1 in front, is going to cancel and give me just x squared minus 1 is equal to e to the 4th. And now I can go ahead and solve for x by adding the 1 to the other side. So I have x squared equals e to the 4th plus 1. And solving for x by taking the square root of both sides and then keeping plus or minus. So I have x equals plus or minus the square root of e to the 4th plus 1. So this quadratic equation, because it was missing its x term, I can go ahead and solve it by simply isolating x squared and then taking the square root of both sides. So I have plus or minus, I have two different possible solutions, the square root of e to the 4th plus 1. So in both of these cases, both the positive and the negative aren't going to create a problem inside the original logarithm. So here I'm taking those values, positive and negative, and squaring them. So squaring them is going to make them positive, that's fine. So as long as it's greater than 1, I'm not going to have a problem. And this number is definitely going to be greater than 1. So we have e to the 4th, that's like 2 point something, 2.7 to the 4th. So let's just even say 2 to the 4th, that's already 16, plus 1, that's 17. And the square root of 17, that's bigger than 4. So this number here is going to be bigger than 4, and then we're squaring it. So subtracting 1, still going to make it positive. So we need to have some number sense in order to check our possible solution. So both of these do work. We have plus or minus the square root of e to the 4th plus 1. And quick note, I cannot take the square root of each piece. That's not a property of square roots. The square root or roots or powers do not distribute over addition. So this is the best that I can do here in terms of my solution. So don't just always throw out negative values. We have to check whether substitution of those negative values creates a problem. And in this last logarithmic example, I have solved the natural log of e to the natural log of the quantity x plus 6 minus natural log of the quantity x plus 2 equals natural log of x. So here, to start with, I want to be able to see that right away I have natural log of e, so those actually cancel out. Or the other way you can think about it, doesn't really matter, e to the natural log cancels out. So you can either think about crossing out the ln and the e, so this first term is ln of the quantity x plus 6, or you can think about this e to the natural log cancels out. Either way, I start out with natural log of the quantity x plus 6 as my first term, minus natural log of x plus 2 equals natural log of x. So here, I definitely have more than one natural log to begin with. So in the ideal situation, I want just one natural log, so I want to start thinking about how I can combine these together. Well, on the left-hand side, I have natural log of both of them are natural logs, so they have the same base, and they are subtracted. So my log properties allow me to combine the left side into one log. So natural log of a quotient, and x plus 6 will be the numerator of the quotient, and x plus 2 will be the denominator of the quotient. So I have natural log of the quantity x plus 6 over x plus 2 equals natural log of x. Now, here I have natural log of something equals natural log of something. So in order for the left side to equal the right side, I can simply take the insides and set them equal to one another. So this is equivalent to just solving x plus 6 over x plus 2 is equal to x. I can basically ignore the natural logs. The other way to think about this is I'm exponentiating both sides. So I could think about it as e to the natural log of the quotient x plus 6 over x plus 2, and then e to the natural log x. So the idea being that the e and the ln, e raised to the ln, cancel, and I just have the insides. But I don't even really have to show that part. It's like understanding if you have an equation, the only way the left side can equal the right side, if they're both ln, is if their insides are equal to one another. So now we're solving this equation here, which we can solve by cross-multiplying or thinking about multiplying the x plus 2 to the side with the x. So I have x plus 6 equals x times x plus 2. And I'm going to go ahead and move this work. So I have x plus 6 equals x squared plus 2x. I have a quadratic equation, so I'm going to start to move everything over to one side, set it equal to 0. So I have x squared. I'll have just plus x because I'm going to subtract the x over. 2x minus x is x. I'm going to subtract the 6. And now I want to go ahead and factor this. This one's a nice one to factor. It's just the quantity x plus 3 times the quantity x minus 2. So I get two possible solutions, x equals negative 3 and x equals positive 2. Now I have to check whether these values will make any of the original functions insides of the logs, right, end up being negative inside there. So negative 3 is definitely a problem because on the right hand side I had a natural log of x and I can't put a negative 3 in there. So there's no point in checking the other ones, even though, yes, it doesn't make this one work either. Negative 3 plus 2 is negative. But it does make the first one work, but if it makes any of them not work, then I throw it out. So negative 3 is not a solution, but 2, let's check. 2 is fine. So natural log of 2, 2 plus 2 is 4, 2 plus 6 is 8. So positive 2 ends up working out. So I have just one solution to this logarithmic equation, and it is 2. So we've kind of touched on a lot of different examples here. When there's just one logarithm in the equation, it's pretty straightforward. We want to get that logarithm by itself and either exponentiate or rewrite using the definition of an exponential conversion to a log back and forth. If there's more than one log, we want to start to combine using our log properties. And if I have the same logarithm on both sides, just one logarithm definitely needs to be 1, so we had to combine the left side. So if I have natural log of something equals natural log of something, then I can just simply set the insides equal to one another and solve. So the biggest thing is that we do have to check our solutions because the domain of natural log has to only be positive numbers inside of the logs. Now let's go ahead and talk about exponential equations. An exponential equation is an equation containing a variable in the exponent. So here are some examples. Something as simple as 4 to the x equals 64 is an exponential equation. We can also have 3 to the quantity 1 minus 2x minus 4 equals 10. Or e to the 2x minus e to the x minus 6 equals 0. So in this last one, I have two different exponential terms with an x in the exponent. Let's review some strategies for solving an exponential equation. If possible, we'd want to rewrite one or both sides to have the same base. So b to the f of x equals b to the g of x. Because then, since they have the same base, we can set their exponents and solve f of x equal to g of x. If only one side has an exponential, so something like b to the f of x equals just a number, we can use the definition of a logarithm to rewrite the problem. So we could rewrite it as b to the y equals x is the same as y equals log base b of x. Or we can think about it as taking log base b of both sides. Now, if each side is written as a single exponential function, we can take the common log or the natural log on both sides of the equation to get the variables out of the exponent. So once we introduce logarithms, then we can use those logarithmic properties. So note, we may need to use some other algebraic strategies to solve these problems. So there's more strategies that come with solving an exponential equation. In our first examples, we're going to solve each of the following exponential equations by writing each side with the same base. We'll start with 5 to the quantity 3x minus 6 minus 25 equals 100. So we have just one exponential term here, and I want to isolate that. I want to get it by itself. So I'm going to add the 25 to the other side. So I have 5 to the 3x minus 6 equals 125. And now what I want to recognize is that I can rewrite 125 so that it is 5 to a power. So I can rewrite both sides to have the same base. The left side already has a base of 5, so it's 5 to the 3x minus 6, but the right side can be rewritten as 5 to the third. So now, since they have the same base, I can essentially set their exponents equal to one another. So I can solve when is 3x minus 6 equal to 3. So I can add the 6 to the other side, so 3x is equal to 9, and divide both sides by 3, and I get x equals 3 as my solution. Now we don't have to check domain issues, because exponentials, the domain is all real numbers. Now just to go back to the step where I can set the exponents equal to each other, I don't have to show it, but what's really happening here is I can think about this as taking a log of both sides, taking log base 5, I'm going to squeeze it in here, log base 5 of both sides. So I'm not multiplying both sides, I'm taking log base 5 of 5 to the 3x minus 6, log base 5 of 5 to the third. Since they have the same base, we just have the exponent left over. So we don't have to show that step, but that's why we're basically able to ignore the 5's in the base. They're the same base. So now, in this next example, I have 1 over 9 raised to the x equals 27. And I want to think about how can I rewrite each side so that they have the same base. Now here, 1/9, I can think about that as 1 over 3 squared. But if I bring that 3 to the numerator, it's going to be 3 to the negative 2. So this left-hand side is 3 to the negative 2, and then raised to the x. And 27 is 3 cubed. So I do have them written with the same base, because the left side is 3 to the negative 2x. Those exponents multiply by properties of exponents, and then equals 3 to the 3. So now we can set those exponents equal to one another, or the idea of taking log base 3 of both sides will get us just negative 2x equals 3. So we have x is equal to negative 3 over 2. I want to make sure we keep that negative there. So we're just setting those exponents equal to one another, provided that we can write both sides with the same base. So I have negative 3 over 2 as my answer. And again, the nice part is I don't have to check. These next examples still have the same set of instructions. We want to solve by writing each side with the same base. So here I have 8 to the quantity x plus 2 equals 16 to the x plus x. Well, first things first, I can add the two x's and the exponent together. So what I have is 8 to the quantity x plus 2 equals 16 to the 2x. X plus x is 2x. So now, to rewrite these with the same base, the base I'm going to use is 2, because I know my powers, and I know that 8 is 2 to the third, and that's to the x plus 2, and then 16 is 2 to the fourth, and that's to the 2x. Now here, we have to make sure to multiply the exponent of 3 to the exponent of x plus 2, all in parentheses, so the 3 is going to distribute. I have 2 to the 3x plus 6 power, and on the right side, 2 to the 8x. So we're multiplying 4 times 2x. And now, since they have the same base, I can go ahead and set their exponents equal to one another, sort of thinking about taking log base 2 of both sides leaves us just with the exponents. 3x plus 6 is equal to 8x. Or we have 6 is equal to 5x if I subtract the 3x to the other side. So that leaves me with x equals 6 over 5. So I'm going to solve for x, divide both sides by 5. So 6 over 5 is my solution. So we have just some places for common mistakes here. Turning x plus x into x squared is a common mistake, and not realizing that I do have to multiply 3 times x and 2, that the 3 distributes. And now in this example, I have e to the negative x squared equals e to the 2x over e cubed. Now clearly we can see that we want to rewrite each side with a base of e. The right side is the part that's presenting me with an issue, so I have e to the 2x over e cubed. But my properties of exponents will allow me to rewrite the right-hand side as e to the 2x minus 3. So if I want to bring e to the third to the numerator, it's changing the exponent to a minus 3. So I'm subtracting 3 copies of e from the top, which has 2x copies of e. So e to the 2x minus 3. And now they have the same base, so I can set the exponents equal. So I get negative x squared equals 2x minus 3. It's a quadratic equation. I prefer to have a positive x squared, so I'm going to add the x squared to the right-hand side. X squared plus 2x minus 3. And this one's an easy one to factor. We get x plus 3, x minus 1. So my two solutions are negative 3 and positive 1. And again, because we're talking exponentials, there is no domain restriction, so both are solutions. In this next example, we're told to solve 7 to the x equals 12. And we can't use the previous strategy. There's no way to rewrite both sides so that they have the same base. Now here, we only have one term with an exponential. I have 7 to the x on the left-hand side equals a number. So what I can do to solve is think about rewriting this as its logarithmic equivalent. So to get the x out of the exponent, I can think about this as log base 7 of 12 is equal to x. So to rewrite this as a log, 7 is the base of the exponential, becomes the base of the log. The output of the exponential is the input of the log, and the exponent is what the log equals. So there we have it. X equals log base 7 of 12. That's the answer. And that's one way of thinking about it, log base 7 of 12. Now I'm going to present you with different ways to solve this exponential equation. So I'm going to go ahead and rewrite 7 to the x equals 12. The other way I could have thought about getting that x out of the exponent is by taking log base 7 of both sides. Log base 7 of 7 to the x and log base 7 of 12. Because log base 7 of 7 to the x will cancel and just give me x by my properties of logs. So there we have, again, the same answer, right? Log base 7 of 12. I'm going to give you one more way to solve this same exponential equation. So we start with 7 to the x equals 12. Now the issue is that I have an x in the exponent. So we want to introduce logarithms to get rid of the x in the exponent and bring it to the front. Now I can't just bring it to the front of the 7. Sometimes students do that early on and they confuse the different properties. I can only do that when logarithms are involved. So let's involve one of our special logarithms, either the natural log or the common log. It doesn't matter. So let's say I want to take the natural log of 7 to the x of both sides, because whatever I do to one side, I have to do to the other. So I've chosen to take natural log of both sides. Now that's not going to cancel natural log and 7 and just give me x. It will allow me to drag the x to the front of the log. So x times natural log of 7 equals natural log of 12. Well, now I want x by itself. I have x times natural log of 7, which this is just a number. ln 7 is a number, so I can divide by it. So I'll have x equals natural log of 12 over natural log of 7. So we have x by itself. But you might be thinking it doesn't look like the first two answers. But it does. Natural log of 12 over natural log of 7, if we apply our change of base formula, this is log base 7 of 12, because the 7 goes in the base and the 12 goes inside the log. So we do in fact end up with the same answer, log base 7 of 12. In this example, I want to solve 2e to the x squared minus 50 equals 150. So I'm going to go ahead and isolate the term with the exponential in it. So I'm going to add the 50 to the other side. So I have 2e to the x squared equals 200. Then I'm going to go ahead and divide by 2. So I don't want a number besides 1 in front of my exponential. So I have e to the x squared is equal to 100 if I divide both sides by 2. And so now I can't rewrite these with the same base. So I can use any strategy from the previous ones that we just reviewed. So I can rewrite this using the definition of a logarithm. I can take the natural log of both sides, or the common log of both sides. But here, the obvious choice would be to take the natural log of both sides, because this idea of e and natural log being inverses. So I'm going to take the natural log of e to the x squared equals the natural log of 100. And now natural log and e cancel and give me just x squared equals natural log of 100. So x is equal to plus or minus the square root of the natural log of 100. And there are no domain restrictions, so both of these are my answer, plus or minus the square root of ln of 100. And we can't take the square root of 100. So this is all one quantity that I'm taking the square root of. This next example has us solve e to the 2x minus 4e to the x plus 3 equals 0. And this one's a tricky one. It's just going to take practice to recognize that what this looks like here is it looks like a quadratic. This is what is called in quadratic form. So essentially what I have here is I have e to the x squared minus 4e to the x plus 3 equals 0. So I want to kind of think about this as having like x squared minus 4x plus 3 equals 0. So instead of x, though, it's an e to the x, but it has that same form. So here I would factor to solve this quadratic, right? I would factor to x minus 3, x minus 1 is equal to 0. Well, we're going to use that same idea to factor on the left-hand side. So I have e to the x minus 3 as a quantity and e to the x minus 1 as the other quantity. So with practice, you'll be able to tell that this is in quadratic form and that to solve it, we would factor it. And now I have two factors set equal to 0, so I can set each one equal to 0. E to the x minus 3 equals 0, and e to the x minus 1 equals 0. And solve each one separately. So here, I would add the 3 to both sides. E to the x equals 3. Here, e to the x equals 1. And now, I'm going to take the natural log of both sides, because to get rid of e, I'm going to take the natural log of e to the x and the natural log of 3. So I end up with just x equals natural log of 3. And then same thing here, natural log of e to the x equals natural log of 1. So I get x equals natural log of 1. But natural log of 1 we can evaluate, right? Natural log of 1 is 0. So I have two solutions here. I have 0 and the natural log of 3. So this work over here, this was just scratch work, and you really didn't even have to do it. I just wanted to show that parallel, that it's just like factoring a quadratic. That's how we ended up with e to the x minus 3 times e to the x minus 1. So one of the early common mistakes that students will make with this problem is they'll see the e, and there's some understanding there because they'll know and understand, well, to get rid of e, I want to take the natural log. But I can only do that if I have e by itself on one side of an equation. So e to the x equals 3, I can take the natural log of both sides. But here, I cannot take the natural log of each thing. So that's a very common mistake when you see more than one exponential. Students will want to take the natural log of this piece and the natural log of this piece, and maybe even just these two pieces, because those are the ones that have e's in it. But I can't pick and choose what I take the natural log of. So I have to have one exponential, right, with a 1 in the front, in order to take the natural log of both sides. I can't just randomly put it in front of e because I know natural log and e cancel. I still have to follow the rules of algebra, which is if whatever I do to one side, I have to do to the other side. I can't just e a bunch of things. And remember that natural log doesn't distribute, right? Logarithms do not distribute. In this example, I want to solve 3 to the quantity 2x minus 1 equals 4 to the x. Now here, the problem is I can't rewrite these with the same base. That's the first thing I would try. But the only thing I can do is rewrite 4 as 2 squared, but this base is 3, so that's out. And then I might try to maybe take log base 3 of both sides. But because they're both exponentials on each side, that's only going to help the left side. So in other words, don't write this down, I could take log base 3 of 3 to the 2x minus 1, but then I'd have to take log base 3 of 4 to the x. Whatever I do to one side, I'd have to do to the other. So that only helps the left side. So 2x minus 1, and then I still have an x over here. So that doesn't really help me, and I shouldn't take log base 4 of both sides because that's not going to help the left side. And sometimes students think they're getting clever and they take log base 3 of one side and log base 4 of the other side, but remember, whatever I do to one side, I have to do to the other. So that's out. So what I'm stuck doing is taking either the natural log or the common log of both sides, right? At this point, it doesn't matter. Since last time we did natural log, this time I'll do common log. So log of 3 to the 2x minus 1 and log of 4 to the x. And what this is going to allow me to do is bring those exponents to the front of the logarithm. So now I have 2x minus 1, notice I'm keeping it in parentheses, times log 3 equals x times log 4. Now here, I no longer have the x in the exponent, so that's great. But now I have these two x's that I have to combine together somehow. So the strategy is going to be, I need to collect like terms. But in order to do that, I'm going to have to distribute log 3, which is just a number, into each term of the binomial over here. So in other words, this becomes 2x times log 3 minus log 3 equals x times log 4. Because remember, log 3 is just a number. So kind of think about it as having 2x minus 1 times 3. Well, what would the natural thing to do be? Distribute in the 3. It's the same idea. Log base 3 is just a number. So we distribute it in. And that will allow us to collect like terms. So I want to keep the two terms with x's, or I want to get them to one side of the equal sign, and the term without an x on the other side. So I'm going to keep 2x log 3 on the left, and subtract x log 4 to this other side. I'm going to move it over, and then I'm going to add log 3 to the other side. So I'm just collecting like terms, like I would with any other equation. It's just that we have to remember log 3, log 4, those are just numbers. Now here, in order to get x by itself, I'm going to factor x out of both of these terms. So I have x times 2 log 3 minus log 4 is equal to log 3. So now I have x times this quantity, meaning I can divide by it to get x by itself. So remember, don't lose sight, we're solving for x. All right, so I'm going to divide both sides by this quantity. So let's bring our work up here. I have x is equal to log 3 all over 2 log 3 minus log 4. So I've solved for x. The only question is, can I do any more simplifying? And the answer is yes. Yes, I can. So I can apply log properties. I can pop this 2 to the exponent of the 3 here, making this log 3 in the numerator over log 9 minus log 4. So 3 squared was 9. That's where that was coming from. Now on the bottom, I have 2 logs being subtracted. They have the same base. They are the common log. So the bottom can turn into 1 logarithm. It's log of 9 over 4. So the 9 goes on the top, the 4 goes on the bottom, right? A difference of 2 logs becomes the log of 1 quotient. And then finally, to get 1 log as the answer, I'm using the change of base formula. So I'd have log with a base of 9/4 and the inside of 3. So my final answer for x as 1 log is log base 9 over 4 of 3. So this is my solution.
In this example, we want to solve 4x squared e to the x minus 36e to the x equals 0. So now we have an equation that involves an exponential function and a polynomial function. So what we want to go ahead and do is apply the strategy of factoring. So we have a common factor here. So we actually have 4 in common in both terms and the e to the x in common in both terms. So I'm going to factor out a 4 e to the x, and I'm left with, in the first term, just x squared. In the second term, I'm left with minus 9 is equal to 0. So now that I have a product equal to 0, I can set each piece equal to 0. So I have 4e to the x equals 0, and then x squared minus 9 equals 0. So we can solve this by factoring to x plus 3, x minus 3, or adding the 9 to the other side, and then saying x is plus or minus 3, which is the square root of 9. And then over here, I can divide by 4, so I'm really solving when does e to the x equal 0. So here, at this step right here, I'd want you to be able to recognize that this has no solutions. It's not possible to raise e to a power and get out to the number 0. If you forgot that and you wanted to just move along with the process of how would I solve for this x, well, I could take the natural log of both sides, natural log of e to the x, natural log of 0. Then you get x equals natural log of 0. So here is where you'd recognize I can't take the natural log of 0. I can only substitute in positive numbers for natural log. So this is not an answer, and so there's no solution to this piece of e to the x equals 0. So my only two solutions are -3 and +3. Another way we can think about this to help reinforce the concept is to think about the graph. Remember that the graph of e to the x, the exponential function, looks like this. So this is the graph of e to the x. So here, where does e to the x equal 0 is like asking where does it cross the x-axis? Well, it doesn't. E to the x is always above the x-axis. So this is another way to think about and confirm that there are no solutions to this piece. In this next example, we have an exponential inequality. Solve x e to the x is greater than 9x. So the first thing I want to call out is that I cannot divide both sides by x. Remember, I can't divide by a variable or I will lose solutions. So what I want to do is subtract the 9x to the other side to start the problem. So x e to the x minus 9x is greater than 0. And similar to when I have a quadratic inequality or a higher degree polynomial inequality, I want to find the zeros first and then create a sign chart to do a sign analysis, especially because I can't graph this. I don't know what the graph of this function looks like. So let's go ahead and factor. So I'll take out an x. I have e to the x minus 9 is greater than 0. So let's take a second to find the zeros. So I would set x equal to 0 and set e to the x minus 9 equal to 0. So e to the x is equal to 9. And then we'll take the natural log of both sides. So we have x equals natural log of 9. So these are my two zeros. These are my two values that I'm going to put along my number line to create a sign chart. So I'm going to go ahead and start my sign chart. It's going to extend from -infinity to infinity, which would be the domain of this function. I can plug in any real number into x e to the x minus 9x, and then I'm going to plot my two zeros. So I have 0 and natural log of 9. So these are zeros. I'm going to put a little z to remind myself of that. And then what we want to do, of course, is go ahead and choose test point values. So between -infinity and 0, we'll go ahead and choose -1. Now here, what's between 0 and natural log of 9? So natural log of 9, we don't need to know its exact value. I mean, just an approximation will work. So if I think about, let's go ahead and look over here for a second, natural log of 9, we are used to plugging in values with e involved into natural log to be able to simplify it kind of easily. So in other words, something like natural log of e squared, I can simplify that. That's just 2. So how does something like natural log of e squared compare to natural log of 9? Well, e is 2.71, so this is like 2.71 squared is approximately 2, and 9 is 3 squared. So natural log of 9 is natural log of 3 squared. So that means that 2 must be between 0 and natural log of 9, because natural log of 9 is a little bit bigger than natural log of e squared, because 3 is a little bit bigger than e, which is like 2.71. So we can pick 2. I mean, the even easier value to pick would be to pick 1. But we do have to have a general sense of what this number is, because to pick a number on the right-hand side, I would need to know, okay, well, this was about 2. Let's go ahead and pick 3 on the right-hand side of natural log of 9. I know for sure that that's going to be bigger. Okay, so now let's go ahead and we plug these test points into the factored version of the left side of the inequality. So we're going to plug these into x e to the x minus 9 to do a sign analysis. So if I plug in -1, that's going to give me a negative. And if I plug in -1 here, so e to the -1, that's going to be 1 over e, so like 1/2-ish, minus 9, that's going to be another negative number. So we have a negative times a negative. Overall, this interval is positive. Here, if I plug in 1, that's going to give me a positive for the first term. And then e to the 1, that's just e, which is like 2.7 something, minus 9, that's a negative. So we get a negative quantity in the middle. And then if I plug in 3, I'm going to get a positive number, and then e to the third, minus 9. Okay, so let's think about e to the third. Again, e was like 2.7 something, or like 3, let's just say, to the third. So that's going to be around 27 minus 9, so that's going to end up giving me a positive value. So we had to approximate things, right? We're plugging in -1, 1, and 3 into e, right? So like e to the -1 was 1 over e, so that's like about a half, right? And then e to the 1, well, that's, you know, about 2.71. E cubed, that's about 27. So it all just comes down to knowing approximately the value of e. So this last interval is positive. We wanted our positive intervals here, so we're going to say that our answer extends from -infinity to 0, not including 0, because I want to be greater than 0. This is equal to 0. And everything from natural log of 9 to infinity. I don't want to include natural log 9. Again, I want to be greater than 0 only. So this is my solution set. In this example, I have solve x squared natural log x minus natural log x is greater than 0. So I already have everything on one side and 0 on the other side of this inequality. So I'll go ahead and start by recognizing that natural log of x is in both terms, so I can factor it out. Natural log x times x squared minus 1. And then x squared minus 1 factors further, so we get natural log x, x minus 1, times x plus 1, so the difference of squares. And then remember, to solve an inequality, again, especially one that we cannot graph, we want to use a sign analysis, so we need to find the zeros. So we need to set each factor equal to 0 to find those zeros to put on our number line. So 2 of them are really easy to solve, although they're not that bad in the first place, even the first one. Natural log x equals 0 is going to be solved by using the exponential e, because e to the natural log x, e to the 0, exponentiating both sides, will get us our x by itself. E to the natural log, or inverses, they cancel. So I get just e to the 0, which is 1. Or we could have just done this by knowing that natural log of 1 is equal to 0, so x is equal to 1. So I happen to get the same value out. I have 1 and -1 as my zeros. So now, here's where we want to be a little bit careful about creating our number line. Our number line should span the domain of the function. Well, the function involves natural log of x, and we can only plug positive numbers into natural log x. So this number line really should start at 0, not including 0, and go all the way to infinity. Oops, let me put an arrow here. And go all the way to infinity. I shouldn't include any negative numbers on this because I can't plug negative numbers into natural log. So I want to go ahead and start at 0. Now, if I had mistakenly, continued this and put negative infinity and plotted -1 over here because that's a 0, I would realize really quickly that I have a problem, because as I pick the test point, like let's say -2, if I try to put -2 into natural log, I go like, oh, can't do that, whoops, so that's an undefined interval. So you would catch it at some point, hopefully, if you went ahead and just made everything negative infinity to infinity, but we should really take a second to think about first the domain of the function, so we don't waste time. So here we have 0 to infinity. We'll pick a test point. Whoops, actually, sorry about that. We'll label our 0. Forgot that there was a 0 in there that works. We have x equals 1, so that is a 0. Now we'll go ahead and pick our test point. Let's go ahead and pick, how about 1/2 and 2. And then we're going to go ahead and plug those into our factors to do our sign analysis. So we're plugging into natural log x, x minus 1, x plus 1. So here, natural log of 1/2, we want to be really careful about this. So you might be thinking, I don't see any negatives, so natural log of 1/2 must be positive. But natural log of 1/2 is actually a negative value. So we can actually look at a graph really quick to do an analysis on this. The natural log graph looks like this. This is y equals natural log x. Here's natural log of 1. So notice 1/2, if I find the y value, that's a negative number. So natural log of 1/2 is negative. So in this sign analysis, we have a negative for the first piece. 1/2 minus 1, that's another negative. And 1/2 plus 1, that's a positive. So two negatives give me a positive overall. This is a positive interval. Then I'm going to go ahead and plug in 2 into natural log. So if I plug in 2, well, I can see plugging in 2 will give me a positive value on the graph. So we have a positive, 2 minus 1 is positive, 2 plus 1 is positive. So this entire number line is positive, right? All the way across, this entire thing is positive, except at 1 where I'm equal to 0. So I don't want to include 1 in my answer. So my answer is going to look like all x values from 0 to 1, not including 1 because that's where I'm equal to 0, not greater than 0, and everything from 1 to infinity. Okay, so we were analyzing the values of natural log on the graph of the natural log of x. So it's definitely beneficial to know your graphs. This is a graph that you should definitely have down. It comes up a lot in future math courses as well. If we wanted to do a numerical understanding of if this is positive or negative, or plugging in some values here are positive or negative, what are the types of values that we can plug into natural log x? So again, values with e involved are the ones that we can easily substitute in because natural log and e cancel. So another test point that you could have chosen over here is 1 over e, because if you plug 1 over e into natural log x, so you get natural log of 1 over e, that's natural log of e to the negative 1. Natural log and e cancel, so I get out a negative value, right? So that also verifies that any point that you choose between 0 and 1, any x value will give you a negative value in the output of natural log. Or here, something that's bigger than 1, I could have chosen e squared over here. And then natural log of e squared, that's just 2. So that's a positive number. So we can do it numerically by testing values that we know how to evaluate on the natural log function, but knowing the graph just makes it that much simpler. Anything between 0 and 1 on natural log is negative. Anything past 1 on the natural log graph is going to yield a positive number.